section 2.3, the completeness property of the reals. The completeness property of the reals. Our plan is as follows. We'll talk about bounds, upper bounds and lower bounds. We'll talk about the concepts of a supremum, that of an infimum. We'll talk about, we'll look at some examples. And then in the end, I will introduce the completeness axiom. Completeness axiom. All right, so let's get started with some definition. Let A be a subset of the reals which is not empty. We say that little l as a real number is a lower bound of for A if for every little a in the set A, little l is less or equal to A. All right, so as an illustration, let's take the example. Let A be the sets -1 to 1. What is this? This is the set of all real numbers satisfying the following condition. And maybe let's illustrate. Let's draw a picture here. This is -1 and this is 1. And so we have every element in the set looks like this. Now let me pick, let's say 0 here. As you can see, for any A in the set A, we know that the membership requirement is that -1 is less or equal to A, which is less than 1. And since 0 is less than -1, which is then less or equal to A, we conclude that 0 is less or equal to -A. As such, 0 is a lower bound for A. And notice that there is really nothing special about 0 here. I could have picked another number like let's say -billion, and we would have arrived to the same conclusion. All right, so next definition is regarding upper bound. Let A be a subset of the real such that A is not empty, and we say let U be a real number. We say that U is an upper bound for A if for any little a in big A, U is less or equal to A. As an example, let's say we consider let A be the discrete sets containing -1, 0, and 1. And let's say U be equal to 1. Then you can see that -1 is less or equal to 1. You can see that 0 is less or equal to 1, and 1 is less or equal to itself. So for any little a in A, we have that little a is less or equal to 1, thus 1 is an upper bound for A. Definition: let A be a subset of the reals, and of course assume that A is not empty if A has at least one upper bound. We say that A is bounded above 2 if A has at least one lower bound. We say that A is bounded below 3 if A has an upper bound and a lower bound. Then we say that A is bounded, period. All right. So otherwise, a set which is not bounded, what does this mean? It means that one of the following is true. Either A is a set A which is unbounded, meaning that either A is unbounded below, or A is unbounded above. Then we simply say that A is unbounded. Okay, so to illustrate these concepts, let me introduce a few examples. First, let A be the set containing 1, 2, 3, let's say 4 and 5. Then clearly this is so A, since A is bounded, bounded above and below, then A is a bounded set, right? Okay, so on the other hand, if I consider the set A negative infinity to, let's say, -1, which is the set of all real numbers such that x is less than -1, then this set, this has no lower bound, right? So A is also unbounded. Suppose next that A is the set containing 1, let's say -1 union 2 to infinity. Maybe here's a nice picture for the set, something like this. You have -1 here, and then we have 1, and then you have 2 all the way till infinity. Okay, so you can see here that this set is unbounded because it is only bounded below and not above. Uh, Here's another example. Suppose A is negative infinity to negative 2 union 1 to 3 union 6 to 8. Let's see, negative 2, 1, 3, let's 6 here. So these sets contains of course we have to remove 2, remove 1 and 3 and 6. You can see that this set is also unbounded. It is neither bounded below, it's neither bounded below nor it is bounded above. Okay. So let me give you a little bit of intuition behind this concept. So as a remark, intuitively you can think of a bounded set as a set with a finite diameter. What is a diameter for me when I'm thinking about for me the concept of diameter means the longest distance between 2 points in the set. So that's what I define here as a diameter. So you can think of a bounded set as a set with a finite diameter, and you can think of an unbounded set and an unbounded set can be regarded as a set with infinite diameter. Okay. All right. Now this having said that, this, so you can think of, so if I give you a set like let's A be the set negative 1 to 1, and okay, you can clearly 1, 2, 4, and any number larger than 1 is an upper bound for the set A, right? So a set has plenty of upper bounds. However, note that 1 is the smallest real number among all upper bounds of A. This leads us to a new concept, which is that of a supremum. Okay, so what is a supremum? Well, let me write this as a definition. Let A be a subset of the real number which is not empty. We say that a real number U is a supremum for A if two things happen. First, for any element in the set A is less or equal to U. And B, if for any upper bound V of A, U is less or equal to V. So there are really two things to consider here. To be a supremum, first, for U to be a supremum, first, U has to be an upper bound. So the first condition tells you that U is an upper bound. And the second condition is telling us that U is the least upper bound. And this is probably the most important property of the supremum. Okay, and from here on, the supremum of A will be denoted by sup of A. Also, it's worth saying that the supremum represents the least upper bound of A. Thirdly, it is unique. And fourthly, it may or may not belong to A. And this actually distinguishes, this is the main difference between a maximum and a supremum. A maximum is the largest element in the set. However, a supremum does not have to be in the set. The supremum is just the least upper bound. Okay? It does not need to belong to the set. I would like to prove the third remark that I made, that the supremum is unique. Okay? So I claimed earlier that the supremum of a set if it exists is always unique. And to prove this, so let A be a subset of the real such that A is non-empty, and let U and V be two suprema for the given set A. Well, then since V is an upper bound for A, and since U is the least upper bound of A, then it must be the case that U is less or equal to V. And similarly, since U is an upper bound for A, And since V is the least upper bound, of A, then V must be less or equal to U. So we have that U is less or equal to V, which is less or equal to U, and this implies that U must be equal to V, giving us the desired result. Okay. All right. So next, in a similar way, we will define the concept of an infimum of a set. Let A be a subset of the reals, which is not empty, and let U be some real number. We say that U is an infimum for A if two things happen. First, U is less or equal to A for any little a in the set big A. B, U is greater or equal to V for any lower bound V of A. Okay, so we can think of so first the infimum of A will be denoted by inf of A. 2, it represents the greatest upper bound of A. And in fact, the first criterion tells us that U is a lower bound, and this tells us that if you give me another lower bound V, then U has to be bigger than that. Tells us that U is the greatest lower bound. Thirdly, the infimum of A is unique. And also, similarly to the supremum, the infimum of A may or may not belong to A. Okay, so perhaps some examples are in order now. Let A be the open set 2 to 7, which is the set of 4 real numbers such that 2 is less than x, which is less than 7. Then I claim that the supremum of A here is 7. It's the greatest, it's the least upper bound, right? And also, note that 7 is not an element of the set here, right? So this is an example where the supremum does not have to be in the set. Similarly, the infimum of A is 2, and 2 is also not in the set, right? The greatest lower bound to illustrate what is happening here. So we have 2 to 7, right? And if you pick any upper bound, it has to be here, right? All upper bounds are here. This is where all the upper bounds are. All the upper bounds are here. And all of the lower bounds for the set must be somewhere here. This is where all the lower bounds are. And if you now pick the least upper bound, the supremum of 2, 7 is 7, right? And the greatest lower bound is here. So the infimum of the set 2, 7 must be 2. Okay? All right. So notice that perhaps it's worth mentioning here that the set A here has no minimum and it has no maximum. Why? Because the maximum of the set is the greatest element in the set. There is no greatest element in the set because the set is open on the right hand side, and there is no smallest element in the set because the set is open on the left hand side. Okay, let's look at another example. Let's A be the collection of points 1, 3, 5. Then the supremum of A here all right, moving forward, let's consider the discrete set containing 1, 3, and 5. Then it's not hard to verify that the supremum of A here is 5 and the infimum of A is 1. And this is an example where the supremum is actually equal to the maximum of the set, and the infimum is equal to the minimum of the set here. Okay. Let's consider the following example. Let A be the collection of points 2, -2, 3, union 4, 8. Then the supremum of A is 8, and that's an element of the set here. So the maximum is also 8. And however, FA has no infimum. I'm sorry, the infimum has no minimum. However, the infimum of A is -2. And that's not an element of the set. Let's consider the set A, -infinity to 5. And you can see here that the supremum of A is 5, and 5 is not in the set. And the infimum of A does not exist since A has no lower bound. There is no lower bound. Okay, so the next results that I'd like to discuss is related to the characterization of the supremum. So what is this characterization exactly? We'll say that a number U is the supremum of a bounded above set A if and only if 1, U is greater or equal to A for any little a in the set A, and 2, for every epsilon greater than 0 that exists A, which is in the set A, such that u minus epsilon is less than a, which is less or equal to less or equal to u. Right. So as an illustration of this concept, if you consider a set, let's suppose here's my set A, which is maybe it's not bounded below, but it's bounded above. And let's say this is u, which is my my supremum. Then let's so first of all, the first condition is saying that u is an upper bound for the set. Okay, that's clear from the definition. So we need to clarify the second part of this characterization. If you hand me an epsilon, which is a positive number, let's say it's small, and this will be u minus epsilon, right? So notice that u minus epsilon is not an upper bound. Is not an upper bound for my set. This is really the key idea here. So you can find an element A, which is in the set, which is sitting in between u minus epsilon and u. So that really is the idea. So I would like to prove this characterization, that these two conditions completely characterize, in fact, a supremum. Okay, so here's the proof. Okay, so suppose let us suppose that u is a supremum of A. Then for any little a in the set A, u is greater or equal to A. So clearly condition 1 holds. Now, to prove 2, let epsilon be a positive number so that u minus epsilon is less than u. Then u minus epsilon is not an upper bound. This is not an upper bound for A. Why? Because any upper bound for A must be greater than or equal to A. And this is clearly not the case because u minus epsilon is strictly smaller than u. So because it's not an upper bound for the set, by negating the definition of what it means to be an upper bound, so in other words, so consequently, it does not meet the condition u minus epsilon is greater or equal to A for any little a in A. Doesn't satisfy this condition. So that means that there must exist some elements A, little a, in A such that u minus epsilon is less than A. And as A is greater or equal to u, because u is an upper bound for the set, since u is an upper bound for A, then we have that u minus epsilon is less than A, which is less or equal to u as desired. Okay? So this gives us that, so one direction. If U is a supremum of A, then condition 1 and 2 hold automatically. Now let's look at the second, so the other way around. So for the converse of our statements, let us assume that 1 and 2 hold. Okay, then we already know that U is greater or equal to A for any A. So we already know that because of 1. So it suffices to show that U is less or equal to V for any upper bound V of A. So let V be such an upper bound if it was the case that V is less than U, then according to assumption 2, there exists some little a in A such that V is less than A, which is less or equal to U, and this is absurd since V is an upper bound for A. So indeed, U is less or equal to V. And this brings us to the end of our proof. So the condition which we stated earlier completely, in fact, characterize the supremum. All right, so similarly, we'll have a characterization for the infimum. Of an infimum. So we'll say that a number U is called the infimum of bounded below set A if and only if, let me be complete, if and only if 1, U is less or equal to A for any little a in big A. 2, for every epsilon which is greater than 0, there exists little a in big A such that U is less or equal to A, which is less or equal to U plus epsilon. So in other words, if suppose this is my set, let's say, which is bounded below, and suppose this is U. If I perturb U slightly by adding a small number to it, so this will be U. So I perturb U slightly by adding a small positive number to it, so this will be U plus epsilon. And okay, so this is my infimum. Then so U plus epsilon will no longer be a lower bound for the set A. So then you'll be able to find an element A which is sitting in between U and U minus epsilon. And that's really is the idea, is that you can't perturb an infimum by adding a positive number to it and expect it to remain a lower bound. Okay, so the proof of this is very similar to the previous case. So, and I will now reinvent the wheel here. So we'll skip the proof for this result, and this will lead us toward the last step in our lesson, which is about the completeness property of the real. So the completeness property of the real. And as an axiom here, the completeness axiom says the following: every bounded set A has every bounded above set A, so essentially any set which is bounded above, admits a supremum, which is a real number. Okay. So a few things to say here as remark. First, from the axiom above, we can deduce a similar property for the infimum. And what is this similar property? Let me state it completely and clearly. Every bounded below set A admits an infimum in R. An infimum in R. So also the completeness axiom illustrates the stark contrast between the rationals and the reals. So let me unpack this idea a little bit. So first, the rationals and the real have the same algebraic structure. Right, they're both closed under addition and multiplication, right? And so they're both fields. They also have the same order structure. So they're both order fields. They are both ordered fields. However, Q does not have the completeness property. What do that really mean here? Okay, let me illustrate this with an example. Let A be a set of rational numbers such that x is less or equal to square root of 2. Right? So we take all so this is square root of 2, and you take all rational numbers in here. Okay, it's hard to visualize this set. So first note that clearly, as a subset of the rationals, A is clearly bounded, right? A is bounded above, and the supremum of A is sup of A, and that's square root of 2. And square root of 2 is not a rational, right? However, if you give me any subset of the real number which is bounded above, it has a supremum, and that supremum is a real number. And that's one property that the rationals don't have. So we complete the rationals. By completing the rationals, we obtain the set of all real numbers, and that's the completeness axiom. That's what it gives us. We will spend a lot of time really trying to understand what does it mean to be a real number. Right? What is the definition of a real number? Because when you think about it, if one attempts to construct the set of all numbers from scratch, well, you start with the natural numbers, right? The counting number 1, 2, 3, 4, 5, and so on. And then you add the negatives, right? -3, zero. First of all, you add 0 there. So you have 0, -1, -2, -3. You count down and you get all the integers, okay? And then to construct the rationals, you take all ratios of the type A over B, where A is a rational and where A is an integer and B is a non-zero integer. Right? But how do we construct the set of all real numbers from the rationals? That's completely not trivial. In fact, this cannot be done algebraically, and the completeness axiom is what gives us the tool to move from the rationals to the reals. And we will later see that a proper definition of a real number will be the following. We will define the set of all real numbers as the set containing all limit points of rational sequences. Okay? There are two words here which may be unclear. First of all, limit, and then sequence. What does it mean to be a sequence of a rational number? And what does it mean to be a limit point of a rational sequence? We will spend a good amount of time unpacking and understanding this concept so that we can finally be able to write down a correct, complete, understandable definition of what it means to be a real number. And this is why you're taking real analysis. So I hope you show up for next class. Thank you.